Hello everyone, welcome back to the lecture series on magnetism in condensed matter physics. In the previous video, we have discussed about the Landau levels and about their degeneracy. Now in this particular topic, we will talk about diamagnetism of electron gas. In the previous video, we have written the Schrödinger wave equation for 3D electron gas in the presence of magnetic field, and the wave function there was a product of plane waves in y and z direction and a displaced harmonic oscillator along the x direction, with energies depending upon three quantum numbers L, Ky, and Kz, where the cyclotron frequency is directly proportional to the magnetic field. Also, we have calculated the degeneracy of each Landau level as mL square omega c divided by pi h cut. Now, to understand the diamagnetic response of electron gas in the presence of magnetic field, the core idea is by the application of magnetic field, the electron distribution breaks up into a series of Landau levels so that the total energy of the system may change by the application of magnetic field. And this situation is equivalent to a magnetization of the system, since magnetization corresponds to the change in free energy with respect to the applied field. And this will give rise to Landau diamagnetism. And the Landau susceptibility will be given by double derivative of free energy with respect to the magnetic field. First of all, let's try to see the classical treatment. The Hamiltonian of free electron gas is given by half m p minus Ea by c. Here we can use the canonical transformation as pi equal to p minus Ea by c, so that the energy of the system will become half mv square, where v is equal to 1 over m p minus Ea by c. Now, as the partition function is given by summation over I of e raised to power minus ith energy divided by kT, and under the canonical transformation, this partition function, it can be transformed so that it is independent of the magnetic field. So this means that, so therefore, del z by del h will be equal to 0. Now if you remember, the magnetization is given by nkbt, derivative of ln z with respect to the magnetic field. In this case, this will also be equal to 0. So this is an example of Van Leeuwan theorem, which states that in classical theory, the total magnetic susceptibility is equal to 0. But however, quantum theory does lead to a non-zero value of the orbital susceptibility of the conduction electrons. The reason for the difference between the classical and quantum mechanical results may be understood from the following physical arguments. The magnetic field causes each electron to move in a circular orbit whose axis is along the field direction. However, classically the speed of each electron is unchanged and hence the energy is also unchanged. So therefore the susceptibility is 0. Now the circular motion of an electron may be considered to be composed of two oscillatory components, each a linear harmonic oscillator, and in quantum mechanics a harmonic oscillator may have only certain discrete values of energy. So therefore this is the quantum effect that leads to a diamagnetic susceptibility. So now we will treat this quantum mechanical effect quantitatively, and we will derive the magnetic susceptibility value under certain approximations. Now in the previous video we have seen the concept of Landau levels, where the energy levels in the absence of magnetic field were quasi-continuous and becomes discrete when a field is applied it, and these discrete energy levels were highly degenerate. And if you substitute the value of omega c in Gaussian units, you will see that this term is the Bohr magneton. So therefore the energy of this 3D electron gas is now given by 2L plus 1 mu b h plus h square kz square divided by 2m. Here I can call this first term as E perpendicular, which represents the energy in the xy plane. So therefore the change in E perpendicular will be given by 2 mu bh, and you can find it by subtracting the perpendicular energy of nearest Landau levels. You can see the concept of Landau levels by using this figure also. Here in the absence of magnetic field, the energy levels is quasi-continuous, while in the presence of magnetic field, the energy levels are discrete and forms Landau levels. Here you can see that this group of levels of the continuum combines to form highly degenerate discrete level in the presence of magnetic field. So, in the absence of magnetic field, all these energies will be converted into single discrete energy level with a very large degeneracy. And a similar thing happens for other levels also. The energy interval is given by delta E perpendicular here, which is equal to 2 mu b times h. For example, all the quasi-continuum levels with energies from 0 to 2 mu bh now have the energy equal to mu bh with L equal to 0. Now in order to calculate the magnetic susceptibility, apply these following steps. The first step is to write the partition function in terms of magnetic field. And here we can use either the Bose-Einstein statistics or the Fermi-Dirac statistics. For simplicity, we will first start with Bose-Einstein statistics. Now in the second step, we need to calculate the magnetization or Gibbs free energy. And in the final step, we can calculate the susceptibility using this relation. Now it is instructive first to assume the Boltzmann statistics. Here let us try to understand how the negative value of susceptibility will arise in this situation. Here you must remember that in the absence of magnetic field, the lower energy levels will be more heavily populated than the higher ones. Here consider this group of electrons that occupies a given Landau level when the field is applied. Now without a field, the mean energy of these electrons will be somewhat less than the energy of the Landau level. Consequently, with a field, this group of electrons will experience a net increase in energy. Hence, the energy of the whole system will be increased. Now, as the magnetic moment is given by negative of derivative of energy with respect to field, and this derivative is positive, so therefore, the susceptibility in this case will be negative, representing diamagnetism. Now next we will calculate the partition function. Now let us calculate the total number of electronic states for a level with a given value of L and for a range of dpz. And from phase space calculation, it will be 2 into d cube r d cube p divided by h cube, where the factor of 2 comes because there are two electronic states or two spin polarizations. Here d cube r will be equal to volume, so this will become 2v divided by h cube, and in cylindrical polar coordinate d cube p will be equal to 2 pi p perpendicular dp perpendicular times dpz. Now p perpendicular times dp perpendicular will be equal to m times the total derivative of p perpendicular square divided by 2m, and this term will be equal to E perpendicular. So therefore we will get m times delta E perpendicular. And just few minutes back we have calculated delta E perpendicular here as 2 mu v h, so we can substitute it. So therefore the total number of states will be given by 2v divided by h cube times 2 pi into m times 2 mu b h times dpz. Here substitute the value of mu b and dpz, so that this will be simplified into 2veh divided by hc times dkz divided by 2 pi, and this will be the number of states. So that now we can calculate the partition function, which is given by summation over all electrons, then e raised to power minus energy of ith electron divided by kBt, and this will be equal to summation over L from 0 to infinity the number of states times integration from minus infinity to plus infinity of e raised to power minus beta e. Here you can see that in the expression for partition function there is a discrete summation which corresponds to quantized Landau levels, while there is another continuous integration which corresponds to the continuous values of kz. This means that in the plane perpendicular to the magnetic field, the energy levels are quantized, while in the z direction the particle is free. We can solve this partition function by integrating first with respect to kz. Now this first integration is nothing but the Gaussian integration with this term as alpha, so that its value will be equal to under root pi by alpha. So therefore z will become 2 pi m divided by beta h cut square whole under root times 2veh divided by 2 pi hc times the summation over L. Here you can take out this h cut square and put the value of beta, so that you will get so therefore we successfully solved the continuous integration. Now it is time for the discrete summation. Let's try to expand this summation by putting the values of L. You will get e raised to power minus beta mu vh plus e raised to power minus 3 beta mu vh plus e raised to power minus 5 beta mu vh, and so on. Now we can take this first term common out of all these terms, so that you will get, here you can see that this forms a series like 1 plus x square and so on, and whose summation for infinite terms will be equal to 1 over 1 minus x. So therefore this discrete summation will give e raised to power minus beta mu vh times 1 over 1 minus e raised to power minus 2 beta mu vh. Now here we can send this numerator to denominator, and we will get 1 over e raised to power beta mu vh minus e raised to power minus beta mu vh, which is a simpler form of sine hyperbolic function. So this will be equal to 1 over 2 sine hyperbolic of beta mu vh. So therefore the overall partition function will be given by 2 pi mkbt whole raised power half times 2 EVH divided by CH square times 1 divided by 2 sine hyperbolic of beta mu VH. Now in this case, the partition function is a function of magnetic field. So therefore, in this case, the susceptibility will not be equal to 0, as suggested by the classical theory. Now in order to calculate the susceptibility, first of all, let's try to calculate the ln of z, which will be equal to natural log of some constant term times h divided by 2 sine hyperbolic beta mu VH. Here we are interested in functional dependence of magnetic field only, so we will keep other things as constant. So this will be equal to ln of some constant plus ln of h minus ln of sine hyperbolic mu Vh divided by kBt. So therefore, the derivative of ln z with respect to field will be equal to 1 over h minus 1 over sine hyperbolic of mu Vh divided by kBt times cos hyperbolic of mu Vh divided by kBt times mu b divided by kBt. Now we can calculate the magnetization, which is given by nkBt divided by mu naught del ln z divided by del h. And we have calculated del ln z by del h, so we can substitute that and we will get minus n mu b times cot hyperbolic of mu bh divided by kBt minus kBt divided by mu bh. And if you remember from the theory of paramagnetism, this is nothing but the Langevin function of mu bh divided by kBt. So therefore the magnetization in this case will be equal to minus n mu b times Langevin function of mu bh divided by kBt. Now we can calculate the susceptibility under the Bose-Einstein statistics, in which the temperature is very large, or we can say that the magnetic energy is very less than the thermal energy. So in that case, the Langevin function reduces to x by 3 in the first order. So therefore the magnetization is given by minus n mu b times mu b h divided by 3 kBt, and which will be equal to minus n mu b square h divided by 3 kBt. So the susceptibility in this case will be equal to minus n mu b square divided by 3 kBt. And this is known as Landau susceptibility. Now if you remember, under Pauli paramagnetism, the susceptibility was n g square mu b square times s into s plus 1 divided by 3 kBt. And if you put g equal to 2 and s equal to half, then you will get the Pauli susceptibility as n mu b square divided by kBt. So therefore here we get an important result, that the Landau susceptibility is equal to minus 1/3 of Pauli susceptibility. Since both Landau diamagnetism and Pauli paramagnetism are associated with free electrons, so therefore we can say that the orbital contribution of conduction electron is equal to minus 1/3 of spin contribution of conduction electron. Hence we get a remarkable result that, except the negative sign, the diamagnetism is just 1/3 of the spin paramagnetism. This result is also holds for Fermi-Dirac as well as Boltzmann statistics. but it is very difficult to show, so we will skip that. But in the limits of high fields and low temperatures, the Langevin function will be equal to 1, meaning that the magnetic moment will approach a saturated value equal to minus n mu b. But this is not observed experimentally. This difficulty can be removed when the Fermi-Dirac statistic is employed. Actually, it was found experimentally that the susceptibility was an oscillatory function of the applied field. This phenomena is known as the Haas-van Alphen effect, and this can be explained when the Fermi-Dirac statistic is employed. Let's end this topic here, and we will meet next time. Thank you so much for watching this video.